Okay, today we're going to begin the discussion of chemical kinetics. Kinetics is one of the major topics that we cover in Gen Chem 2. We've covered solutions and solution properties, and we cover kinetics next, and then equilibrium, thermodynamics, and some electrochemistry and nuclear chemistry along the way. So today we begin kinetics, and I'd like to talk about the kinetics as the change in concentration of a substance in a reaction divided by the time interval it took for that change to take place. So it's a change in concentration over a change in time. The concentration change may be followed using either a reactant or a product. Now, typically, we're going to begin to think about reactions in Gen Chem 2 as being capable of going both ways. Under some sets of conditions, it would go from left to right, but under some other set of conditions, the net reaction might be right to left. So we have the ability to write the chemical reaction however we want to, but nature will do what it does. And so the reaction we wrote on our paper may not be the actual direction the reaction takes place. So we can follow the reaction using either what we've called a reactant or a product. Because of the stoichiometry, they are related to each other. So now, we're going to talk about the rate of change in the concentration of some species in the reaction, but we're interested in the rate that's inherent with that particular chemical reaction. So since we could all balance the equation with a different set of coefficients and all of us be right, we need a number for the rate of the chemical reaction that does not depend on the way we balance the equation. The way we get that is we can normalize all of the individual ways we could measure the rate by dividing by the balancing coefficient we have used in writing the equation. So you take the change in concentration and divide by the balancing coefficient, and then that should get the same relative number regardless of what we're studying or what reaction we're doing or how it's balanced. Now, the rate of a reaction is by definition a positive number. Bigger that number is, the faster the reaction goes. Now, the rates are controlled by 5 different factors. The nature of the reaction is important. If you take hydrogen and oxygen and mix them together and spark it, it will explode. So that reaction is extremely fast. But if you look at concrete settling, it takes about 100 years for it to be totally complete. Now, it's hard enough for us to walk on and drive on in much less time than that, but the reaction is continuing and will continue for maybe 100 years or so. The concrete will get harder and more brittle, and long before the reaction is over, we'll have to replace it because of cracks and potholes that have occurred before then. It depends on the contact between the reactants. Now, obviously, if you have all gas phase reactions, the molecules are traveling extremely fast in the gas phase, of the order of the speed of sound. So they're traveling very fast and they're hitting each other very frequently. In air, there's probably 10 to the 16th 2-molecule collisions per second. So there's a very fast bringing together of components in the gas phase, and they could react to each other during those collisions that take place. So contact is important. If we go to liquids reactions, then diffusion does occur in liquids, and the collision frequency is not much different in it, but it's in a very localized volume. So it's going to take longer for a reactant to migrate to a spot in the solution where the product, the other reactant is located, so that a reaction can take place. So you do have good contact. Reaction rates within liquids can also be very fast. But reactions between solids are not very fast at all. In fact, they are only going to react along the surface. So the more you grind the particles up to a finer and finer powder, the faster they will react. So we do have to have physical contact between the reactants in order for a reaction to take place. But that contact is going to be pretty fast in gas and liquid reactions anyhow. But between solids, we would want to grind it up and get close, more surface area exposed. It depends on the concentrations of species involved in the reaction. Now, I've been careful with the wording there. Species can be a reactant, it can be a product, it can be something else. For example, if you carry out a reaction in water, water has a small amount of both hydrogen ion and hydroxide ion in the solution. And so sometimes reactions are going to involve the hydrogen ion or the hydroxide ion in aqueous solutions, and the rate of reaction may depend on whether the concentration of hydrogen ion is high or low. So there could be things in the that determine the rate of reaction that really aren't even part of the overall balanced equation. They may cancel out in some place if we look at the individual steps that reactions go through before you reach product. It depends on the temperature. And I like to tell people this, that there's very few times in science where we can say always. This is one of them. Always, the rate increases as you increase the temperature. There's lots of reasons for that we'll get into as we go along. But temperature is one of those 5 factors that we're listing that determines the rate of reaction. The other thing is the presence or absence of catalyst. Catalysts are inhibitors. Catalysts cause reactions to take place faster. Inhibitors cause them to take place slower. Sometimes a reaction that would go and get out of hand and go too fast, we would like to have an inhibitor that would slow it down and make the reaction occur in a more manageable way and less likely to blow up in our face. Now, all of the reactants and products in a chemical reaction are connected through the balanced equation. And we've already learned from stoichiometry that if you know the concentration of one reactant or one product, you can calculate the amount of the all of the other reactant components at once if you want to. If you had Gen Chem 1 with me, I showed you a way to work stoichiometry problems where you actually calculate the amount of everything in the entire reaction all at once. So the balanced equation allows us to connect not only the concentrations of each species as they react, but also the change in concentration of each species. So if we know the change in concentration of one reactant, for example, we can calculate the change in concentration of everything else involved in the equation. For example, if I had this generic reaction, 2A and 3B goes to 4C, suppose the change in concentration of reactant A is 6 moles per liter per minute. If I want to know the change in concentration of B, I can just say, okay, I'm going to take the 6 moles per liter per minute of A. In the balancing equation, there's 2A that react with 2B. I put the plus signs in there to remind us that they're both on the same side of the equation. If one is increasing, the other is increasing. If one is decreasing, the other is decreasing. So it's just a matter of doing a simple mole-to-mole stoichiometry to get the concentration change in B with time is going to be 9 moles per liter per minute if the concentration of A is changing by 6 moles per liter per minute. I'll make a point right here. If this concentration is a positive number, as we've implied here, what is that telling us about the way this reaction is actually taking place? That's right. A is increasing and B is increasing, which means the reaction has to be going from C to A and B. That's the reason for the double arrow here. Now, if I wanted the concentration of C, I can still calculate that from the concentration of A that we were given, 6 moles per liter per minute. And as A is, there's a coefficient of 2, and for C, there's a coefficient of 4. But if A is positive, this one has to be negative. So I put a -4 in there because we had the +2 down here. All right, we cancel out our units and we get -12 moles per liter per minute for the change in concentration of C. So I set this up deliberately to introduce you to the idea right away that we don't always know the direction a reaction actually takes place. Sometimes it surprises us and goes the way, the opposite to the direction we thought it would. Now, as a general rule, the rate of a reaction is going to decrease over time, and you would just think of that. You're going to use up the reactants and form mostly toward products. It may all be products eventually, or nearly all. Now, there is a law that relates the rate of a reaction to various things that are contained in the reaction. It's generally proportional to concentrations of species involved in the reaction. Now, these could be reactants, all of them. They could be reactants and products, or they could be products. It could be a mixture of those. And these A, B's, and C's could even be things like hydrogen ion in water, even though hydrogen ion is not shown in the balanced equation. So these species in the reaction are often and usually reactants, but not always. The coefficients that we raise these to powers are not the balancing coefficients. I repeat, the exponents that we use for each concentration are not their balancing coefficients. It's just an accident if they are. Those little exponents are typically rational fractions. They could be a whole number like 2, but 2 is a rational fraction of 2 divided by 1. So they are rational fractions, generally ratios of small whole numbers. They could be integers. They could be fractions, 1/2, 3/4. Numbers like that typically are not uncommon. And they depend on this specific rate constant. That rate constant is something that we would determine from the kinetics data that we have. That's why we call this an experimental rate law. You can't predict this from the reaction. Now, this is an unsolved problem in chemistry. There have been some very good solutions for very certain cases. But for a general reaction that you could just write down any old reaction you could do in the lab, there is just no way you could calculate its rate or its rate constant. So that's a problem. If you get that, you might get one of those good old Nobel prizes, okay? In order for a reaction with respect to a reactant, the order is a exponent, And it's whatever exponent it is in this experimental rate law. Now, the overall order for the reaction is the sum of all of the little individual orders. Now, loosely speaking, on a collision frequency idea, the order of a reaction tells you how many components have to be assembled during a collision for that reaction to take place. So I told you that bimolecular collisions in air are of the order of 10 to the 16th collisions per second. But if you look at three-body collisions where two molecules collide and a third one collides before those two bounce off of each other, that is much, much smaller. We do get termolecular collisions, an appreciable number, but as you go further and further up, higher and higher orders become less and less probable, and typically result not from collisions involving that many molecules, but from assembling of pieces that ultimately do come together to make products. We'll look at this later on when we study what we call reaction mechanisms, how the reaction actually takes place. Now, there are units to the specific rate constant, and they will depend on the order of the reaction. For example, if I've got a rate, it's always going to be a change in concentration over a change in time. So its units for the rate are going to be moles per liter per unit time. If it's a fast reaction, it might be moles per liter per second. If it's a little slower, maybe it'll be moles per liter per minute or moles per liter per hour, or in concrete, moles per liter per century. So it's moles per liter per unit time. Suppose the overall order is 0. So that can happen. A rate is equal to some constant times the concentration raised to the 0 power. Now, what do you get when you raise any number to the 0 power? By definition, that's a 1. So the rate constant is going to have the same units as the rate did. So units of rate has to be moles per liter per unit time. Now, suppose the reaction is first order. And while here, I want to make a point. We talked about the rate of the reaction, and we're measuring it in terms of A. A's concentration, we say, is decreasing. I had to divide by 2 to get the rate of the reaction because this coefficient 2 had to be normalized out. I could get the same thing if I wrote the change in concentration of B times minus 1/3. That would give me exactly the same number if I'm following the change in concentration of B that I got when I took the change in concentration of A of time and divided by 2. So if I have a first order reaction, it's going to be some constant times concentration of A raised to the first power. Now, the concentration of A is moles per liter. The units for the rate is moles per liter per unit time per second. So the moles per liter are going to cancel out, and K would be just 1 over time. So the specific rate constant will have the units of 1 over time, so that when I multiply 1 over time times moles per liter, I get moles per liter per unit time that I had to have for the overall rate of the reaction. Now let's look at a second order reaction. Again, remember we get this number by measuring the change in concentration over a period of time. Divide that out. I need to divide by 1/2, and I multiply by 1/2. I need to have a negative sign because the change in concentration would be decreasing if it's a reactant. And so I need to get a positive number. That's the reason for the negative signs in all of these. Now, the concentration then has units of moles per liter squared. The rate of the reaction has moles per liter per time. So in order to make this work out, the units on the constant have to be liters per mole per time. Because you see, if I took liters per mole and multiplied it by moles per liter squared, I would just get moles per liter, and then the time is in the constant here. So you see, the units of the specific rate constant depend on the orders of the reaction. Now, I've only showed 0, first, and second order because that's all we're really going to deal with in Gen Chem 2. If you go to physical chemistry, they'll go to more general forms of the second order reaction. We're not going to cover it here, but you could have a second order reaction overall where it was first order in A and also first order in B. And I've been very deliberate in all of these to make sure that I'm not assuming the order is the same as the balancing coefficient. It happened to be true when I did second order in A because I used a 2 up there. Okay, all right. Now, the value of the specific rate constant is going to be one of the important controlling factors in the rate of the reaction. The rate of the reaction is going to be directly proportional to the value of the rate constant. The rate constant doubles, the rate's going to double. It depends on the nature of the reaction. That's where that is. There would be a different kind of constant for a very fast explosive hydrogen-oxygen reaction than there would be with the setting of concrete. So the specific rate constant is going to be determined by the nature of the reaction. It is determined by the temperature, and as we said, it always goes up. The value of the constant will increase if the temperature increases. It depends on the catalyst. If the catalyst is present, the reaction rate constant will be large. If there's an inhibitor present, the rate constant would be small. Now let's look at how you measure rates, and here are some data that we measured concentration of a species, a reactant, I guess. Looks like it's going down, so that must be a reactant. So we take these data and we graph them of concentration on the y-axis and time on the x-axis. And then we've entered the point. At time equals 0, we're at 0.1. At time equal 40 seconds, we're at 0.076. At time equal 80 seconds, we're at 0.045. At 120 seconds, we're at 0.030. And at 160 seconds, we are at 0.02. Now notice I made my graph to include only the region of my data points. If I wanted to go beyond that on either side, I could include that, but my data points would just be in this region. So it's most accurate if you just use a dispersion of your points that allows you to use essentially all of the graph paper. Now, if I were teaching lab and I had you graph some data, sometimes I'll do something really nasty. If a problem's worth 10 points and you use 50% of the graph paper that you graphed it on, I'd give you 50% of the 10 points. Isn't that nasty? But I want you to get used to doing graphing to help you solve chemical problems and give you the best graph with the least amount of error involved in using it. So you want the largest graph that you can make, and this is what we would do. Now, here's something else I want you to keep in mind. You never, ever, ever just draw a straight line, point to point to point to point. Don't do that. That's going to be a serious error in your graphing if you do that. You want a smooth curve between each of the data points. And so you have to have either what's sometimes called a French curve, where you've got several different curvatures along it that you can use to draw this. But you want the best fitting smooth curve that includes your data points. Now, it is possible that your best fit curve would be between some of the points. That's why it's important not to just do point to point to point to point graphs, because you do not want the error in this data point's location. You know, is it here or is it up there or where? You don't want the error involved in graphing that point to affect the data in between the points. So if you've got a smooth curve and this one you measured too high, and this one you measured too low, and this one you hit about right, then the best expected value between these sets of data points where there was error involved would be to use your smooth curve, and that's what you want to do. Okay. Now, if I want the rate over the entire period between 0 and 80 seconds, then I can just take these two endpoints and I can calculate the change in concentration. So I want to take the concentration at 80 and subtract the concentration at 0, and that gives me 0.055. The difference in time is 80 minus 0, so it's 80 seconds. So I can divide that out, and what this will give me is the average change in concentration over this period of time. But if I really wanted the rate at 80 seconds, then what I need to do is take my best fit line shown in green here, and I want to go into 80 seconds and draw a tangent. And the tangent is this line, and this curve have only one point in common. That's the tangent point. And so I'm drawing that tangent at that point, and then I can get the slope of the line is the rise over the run. The difference from here to here is the rise. The difference from here to here is, where it crosses here, is the run. And so I just take those two numbers and divide them out, and that gives me the value of the specific rate constant. Now, that's going to be different from what we got up here. And this would be a better, truer value of what the rate is at this moment in time. In other words, at 80 seconds in time. Let's look at this reaction. This is a combustion of propane, and it goes too fast to ever measure. So I've made all this data up just to illustrate how we use balancing coefficients and so forth in measuring rate. If the change in concentration of propane is minus 50 moles per liter per second, now what is that telling me? Minus tells me it's going from left to right, that the C4H10 really is a reactant, and the reaction, this concentration is decreasing, that's the negative sign, by 50 moles per liter per second. What's the rate of the reaction? Well, remember what we said? You take the change in the concentration over time and divide it by the balancing coefficient. Now, this 1/2 is not something you memorize, okay? The rate is not always 1/2 of the concentration. What if we'd said oxygen concentration change was minus 50 moles per liter? Then what I would have done is I would put the change in 50 moles per liter, but I would be dividing by I'd be multiplying by 1/13 or dividing by 13. So this is not something to memorize. The thing you have to memorize is the rate of the reaction is the change in concentration of a species that you're measuring divided by that species balancing coefficient. So this one has a rate of 25 moles per liter per second if these data were accurate, which they're not, but it's okay. Illustrates the point. What's the rate of change in oxygen concentration? Well, remember, if we have the stoichiometry, we have the equation balanced correctly, if I know the amount of one, I can calculate the amount of everything else. So specifically, if I say, okay, the rate of oxygen concentration is going to be 13 halves of the rate of the propane concentration, right? That's the conversion. So 13 halves of 50 is going to be minus 325 moles per liter per second. And we've got that by just the concentration of oxygen is 13 halves of the change in the concentration of this one. That's the stoichiometry. So you see, I could have also got it from what we did up here. The rate of the reaction itself is 25 moles per liter per second. So if I just multiply that by the balancing coefficient for that, that gives me this one. That's actually an easier way to get all the rest of them. This one would be minus because it's decreasing. If I wanted CO2, I would be taking 8 times 25, and it would be increasing. That would be a positive number. And 10 times 25 would be the rate of oxygen, water change. So we get them all knowing any one of them. What's the change in the carbon dioxide concentration? Well, what we said there, 200 moles per liter per second. Now here's a checkpoint on this. And again, we have a real equation, really can be balanced. In fact, that's one of the ones I use in Gen Chem 1 to see if people can balance difficult equations. So this is an equation that is balanced correctly, I think. So the rate of disappearance of nitric acid is 20 moles per liter per minute. Now notice I said disappearance and I didn't put a negative sign here. Disappearance told me it was negative. If I said the rate of disappearance is negative 20 moles per liter per minute, I would actually be saying by English correctly, it's a double negative. So I would be saying it's positive, increasing. Okay, what's the rate of this reaction? What's the rate of the concentration of carbon dioxide changing, and so forth. Okay, now here's a problem also that we could do. This is a very interesting reaction. It's the key reaction component in one of the many clock reactions. This reaction goes pretty fast, but if you put another component in the solution that uses up triiodide, triiodide is a good oxidizing agent. So if you put something like sulfide ion or something else in there that is easily oxidized, then what's going to happen is you'll use up the I3 as fast as it forms until you've used up all of that other reactant. And the moment that other reactant disappears, I3 minus will appear in the solution. If you put some starch in the solution, I3 minus attaches itself to starch molecules and forms a deep purple color. So the reaction will be water clear, and then at a moment, it'll flick and turn purple. And I've used that as a demonstration sometimes, and sort of like turning water into wine. I know it's going to take 10 seconds to reach that point. So when I mix the reactants together, I'm counting down in my head from 10 to 0. When I get to 0, I put my finger in the solution and voila, it turns purple like wine. I wouldn't drink it though. Okay, but this is the experimental rate law for that reaction. The selenous acid concentration is to the order 1, or iodide ion is to the order 3, and hydrogen ion is to the order 2. Now notice these are not the balancing coefficients except for selenous acid. Okay, what's the order with respect to hydrogen ion? Okay, well, there's hydrogen ion. What's the order? What is the order of the reaction? So I would take 3 plus 2 plus 1 would be 6. When each of the reactants concentration is 0.05 moles per liter, the rate of the reaction is 7.81 times 10 negative 3. What is the value in units of the specific rate constant? Well, we've got the numbers in there. You've got each of these concentrations is 0.05. So 0.05 to the first power times 0.05 to the third power times 0.05 to the second power is 0.05 to the sixth power. And so we'll know this number. We know what the rate is, this number. We solve for K to get this number. What is the rate of the reaction? What rate of reaction is predicted if each concentration is 0.04? Well, now we have the rate, specific rate constant, and we put in 0.04 for each of these concentrations. We solve for the rate of the reaction. So you can do that. Here's a checkpoint that related to that. And we're saying, pretend the rate law is this number. It's not. But we're trying to illustrate kinetics concepts, not, in this case, accurate reactions. I just want to use a reaction so that we know how to handle balancing coefficients and things like that. What's the order with respect to methylamine? Okay, I think this is the methylamine right here, and I think I know what the order is. What is the overall order of the reaction? Well, I know that one and that one. I think I can get that one. And what are the units of the specific rate constant? So remember, once we get these orders, these concentrations, we know what the powers are. We know what this order has to be. The units on rate has to be moles per liter per second or per time. And these have to be in moles per liter to these powers. So we can just solve the problem for K putting in the units. Moles per liter, moles per liter, moles per liter per minute, per second or whatever here, and solve for units of the rate constant. Okay, so that finishes this particular lesson. So what we'll do now is we'll stop this recording and process it, and then I will provide another one for the next PowerPoint lesson as soon as I get time to carry out that reaction. Okay, so let's stop the share here and end. All right, we'll see you guys next time.